Alright, calorimetry. Let's say we drop ice in water. Yes. Let's have like, I don't know, a kilogram of 100-degree water Celsius. And let's drop in an ice cube, a really cold ice cube. The ice cube's temperature is going to be like negative 10 degrees Celsius. And it will be, I say, 0.1 kilograms. Okay, so these problems can be quite tedious if you don't have somewhat of an idea of what's going on. So in this case, I'm pretty confident that this entire ice cube is going to melt, and I'm going to be left with just water, because I have a small amount of ice compared to the water, and the water's really hot. And the ice is only pretty cold. So I'm going to go ahead and assume that I'm going to be left with just water. Now, in some problems, you can't really make that assumption if the numbers aren't so clear, and they're awful. But let's do one of these instead. Okay, so I'm going to draw a few more pictures of what's going to happen. So it'll start out, it'll start out in there, right, with these values, even for a moment before it starts to heat up. And then the ice will heat up until it is at 0 degrees. I'm going to take a snapshot. 0 degrees Celsius ice, right? And the temperature of the water will have heated up a bit. And then, like that there. Okay. And then, well, the ice will melt, right? And it will become like a blob of 0-degree water. Okay, of course this can happen. I mean, you've been in a pool and you've felt hot and cold zones of water. Okay, and now after that blob of water will equalize in temperature with the rest of the water, and we'll be left with this final temperature. So let's find that. Let's find the final temperature. Okay, so from this picture to this picture, the ice is heating up. So we are going to use the equation for that involves the heat capacity. So Q1, shall I say, is M of the ice, C, heat capacity of ice, times the change in temperature. I'll say change in temperature 1 here. Okay. Now here, the temperature is not changing, but we are going through a phase change. It's melting, right, liquefying, and so the heat energy involved here is just the mass of the ice times the latent heat of fusion. Okay, so it's called the latent heat of fusion because somebody had in mind going from water to ice freezing. Well, it's the same number, the same constant if you're going from ice to water or solid to liquid or liquid to solid. Okay, and then we have our ice has turned into water, and it heats up to some final temperature. So Q3 is going to be, well, it's water, but this blob of water is still represented by the mass, what I called the mass of the ice, right? It was ice. So it's the mass of the ice times the C of water, because it's water now, the heat capacity of water, times the change in temperature, 3, I'll say. Okay, so I just tracked the life cycle or whatever of the ice cube here, right? So, I'm assuming that this is a perfect calorimeter that it's in, and we're not losing any heat to the outside world. The only heat transferred is between the water and the ice cube. So the way that we solve this is we know that the heat that goes into the water is from the ice, something like that. We know that the heat energy of the water is equal to negative heat energy of the ice, and you can put the negative on either side mathematically. So all that happens with the water is it decreases temperature, right? Here it is at its initial temperature. Initial temperature of the water is 100, and it goes to some final temperature. It's not It's not melting or vaporizing or freezing or anything like that. So the Q of the water is simply mass of the water, C of water, delta T. Okay, is equal to, well, Q of the ice, which is, well, negative out in front, right? and I already listed out all of the different heat energies of the ice in the different stages. So it's simply the sum of all those. We've got mass of the ice, C of the ice, delta T1 plus okay. I see I've got a mass of ice everywhere that I could pull out in front if I felt like it, and maybe I'll move the negative sign to the other side just to get rid of those parentheses. So negative M. So this delta T over here, that's the final temperature minus the initial temperature of the water. Move this thing over. Mass of the ice. I'm going to leave the mass of the ice there. Mass of the ice, C of ice. Okay, delta T1. So that is going from my negative 10 degrees Celsius ice to, so I don't know, T ice initial, to 0. Right? So that's final 0 minus T ice initial. Okay. Plus the mass of the ice, heat of vaporization of the ice. These L's and C's are all things that we would look up, by the way. The heat capacity, C, or the heat of vaporization, the latent heat, L. Both things that we would look up for ice and water. All right, and now plus, continuing here, we've got mass of the ice, heat capacity of water, because it was water now, times the change in temperature there. So that's going from 0 degrees to final temperature. Okay, T final minus 0, like that. All right, so we're looking for the final temperature. The algebra is always a little bit unpleasant on these, but we can do it. So I see I have final temperature here and all the way over here on each side. So I'm going to factor in to the parentheses, and well, that's what I'll do first. So there's just a 0 here. Okay, and now I'm going to go ahead and group these so that I have the terms with a T final on one side and everything else on the other side. So let's see how I'm going to do that. I'm going to bring this negative 1 over to the left side so that they're positive. And that puts everything else on this side. That. And I can factor out the final temperature here and divide what's left to the other side. So after factoring out the final temperature, it's there, and let me just cheat here. So I factored out these MI, CW stuff and divided it over to the other side. Alright, and so our final temperature can be calculated like that. So, oh God, that looks like an awful mess. But really, this is where you start with every calorimetry problem, right here. We know that heat coming out of one object is going into the other object. Yep, and it just can be more complicated if you've got really cold ice in this case, right? Because the ice has to do 3 things. It has to heat up to a temperature of 0, and then at 0 it melts, and then it's 0 degree water, and that water has to heat up to a higher temperature. Speaking of heating up to higher temperature, my computer is doing that. So I will end this video.